Good afternoon.
Good afternoon, ma'am.
Good afternoon. Good afternoon, Vita. So today, first we will be looking at chapter number 11 again, right? So I want to discuss today the modes of transfer and DMA. Okay, so the modes of IO transfer and DMA. That's what we need to do from chapter number 11. Uh, is my PPT visible? I hope my
Yes,
PPT
ma'am.
is visible.
Yes, ma'am.
Yes,
Okay.
ma'am.
So, so last time we talked about what is an IO interface, an IO bus. We took um, peep into what lies inside a interface register. Then we discussed the various types of IO commands. I told you very important things, and then we talked about the uh, options of having IO bus and memory bus as two separate buses, or same bus with separate control lines, or same bus with separate or totally different buses, right? Or totally same buses, I'm sorry. So the last case where we have the complete same bus along with the control lines is called as the memory mapped IO. And the other two options, that is the option 1 and option 2, are known as isolated IO, right? This is what we did last time. Then we saw certain differences between memory mapped and isolated IO, right? Now I want to start today with the different types of modes in which the input output can be done. Okay, so partially I have done this discussion with you before. You will be able to place it, I'm sure. The first thing that going to be talking about is the program controlled IO. In program controlled IO, so this is something that I've already discussed with you, but when I started discussing interrupt with you, but then I'm repeating it for the sake of completeness and for your revision. So, what happens in program controlled IO is that the input output, which is requested by a user or by a IO device in turn, is completely and at all times directly monitored by the CPU. Okay, that is why it is known as program controlled IO, in the sense that there is a program being executed inside the processor. The processor leaves all other jobs, okay, doesn't do anything else, leaves all other programs, and only gets stuck doing the program controlled IO. Okay, it only keeps on executing the uh, instructions of the IO program, and sometimes uh, when the IO device, let's say, is not available, or if you remember, I told you the use of the buffer register in the interface. So suppose this register, a data register of the interface, is not yet full, so that it cannot transfer the data to the CPU. So at that time, in program controlled IO, what CPU does is that it has to sit idle. Okay, what it keeps on doing is it keeps on just checking this status register for this flag, whether it is set or not. Now, suppose it is not set, then the CPU cannot do anything else. Okay, it simply sits idle, and again, repeatedly goes, and after in the next time cycle again checks for this flag bit. So until this flag bit is set, the CPU just keeps on checking the status register of the IO device. Now once this is set, then the CPU receives the data from the interface of the IO device and puts it into the main memory. And after that, it checks, is the transfer complete? If the transfer is not complete, then it has to repeat the same procedure. Okay, that means it again comes back, checks for the status, that is the next word now available for transfer, is the next data word now available for transfer. So how it comes to know that? From this flag bit. So it keeps on checking this again and again till this becomes full. Then it accepts and then puts it onto the memory. Similarly, when it has to do the output, the CPU reads the data from the memory and puts it on the data bus of the IO device. And now, while the data register gets emptied, that means while the data is passed on to the IO device, again the processor has to set empty, just checking for the flag bit. Okay, so this is what is represented in this flow chart. What this is what the processor does. It reads the data register for the data and checks the flag bit. Now, if the flag bit is 0, that means it is not set, that means the IO device is not yet ready for the transfer. It simply keeps on doing the same thing again and again. You can see that it is stuck in a loop. It is stuck in a loop, okay, thus wasting its very precious time, and also at the same time bringing the throughput of the computer system down, okay, considerably. Now, once only when this flag bit is set, that means the IO device becomes available, the CPU goes and reads the status register. Status register is, why is it read? Because the other important things, as if the word which is being given by the, for example, if the user is typing a character and it is to be stored in a variable x, right? You get the value of x from the user, right? So suppose the user is typing a character and it is to be stored in a variable x in the main memory, then the address of that variable x will be provided by the status register. Okay, so it reads the status register, gets the address of where to transfer, and then transfers that particular data to the main memory. Okay, but please wait, is the job of the CPU finished? No, it's still not finished. Why? Because it has just, after this entire thing and sitting idle for so long, let's say, it has just been able to transfer only one word of data. It still has to check whether the operation is complete. If the operation is not complete, it again has to go through the same loop again, the same procedure till all the data has been transferred word by word to the main memory. Okay, when the operation is complete, only then can the CPU continue with some other program that it was supposed to do. Okay, so this is the program controlled IO. Obvious disadvantage is that the CPU has to be all the time present, directly monitor the, actually directly do the IO input output itself, and therefore the throughput of the system comes down considerably, right? Nothing else gets, everything will get stuck in this kind of a system till the input or output is completed. Now, as opposed to this, you remember I told you interrupt initiated IO is an alternative. So what happens in the interrupt initiated IO is that the uh, IO device, instead of, the CPU gets free from this task. Okay, this loop that you see here. So the IO device, instead of the processor checking the IO device, instead of processor having to check it again and again and again and again and get stuck in this loop, it is the IO device's prerogative now to interrupt the system, to interrupt the processor when it is available, for when the data is there in the data register of the interface of the IO device, right? So in the meanwhile, at least the processor can do other jobs, right? I have explained this to you in quite detail. So we also saw block diagrams of how these transfers were taking place, right? We stored the return address, then we went on to execute the IO program. When the CPU received the interrupt, what happens is that it stores the return address of the process that it is currently executing, either on a stack or at a location in the main memory, and then it goes on to service the uh, IO program, right? And then after it is completed with the IO program, it comes back to the main calling program, right? Not the calling program in this case, the earlier program that it was executing. Calling program is when you execute a subroutine, right? So what is the advantage of interrupt initiated IO? The advantage of interrupt initiated IO is that the CPU gets free from this lock and can do considerable work while the IO device is getting ready to transfer the data, right? The CPU doesn't have to wait, right? Other jobs can be processed side by side. Now, the interrupt initiated IO can be can support a vectored interrupt or a non-vectored interrupt. Now, what is the meaning of vectored interrupt? The vectored interrupt always provides the address of where to branch. That means the address of the IO program, okay, which is to be executed by the CPU. And this address itself, the address of the IO program, the IO program is also known as the interrupt service routine. I think I told you this earlier. So the address of the interrupt service routine is called the interrupt vector. And if while interrupting the CPU, the IO device provides the address of the IO program, the kind of interrupt, this kind of interrupt is known as the vectored interrupt. If it doesn't provide the address, it is known as the non-vectored interrupt. Okay. Now, the third option to program controlled and interrupt initiated IO is that uh, we allow for a direct memory access. Now, what is this? Please see, even in the interrupt initiated IO, what is the advantage that we are getting? The advantage is that the CPU is free from this loop. Okay. All the remaining job it has to still do on its own. That means it has to actually do the input output transfer itself. Okay. So only the waiting time for the IO device is reduced. Okay, so again it checks for whether the operation is complete or not, and again, again goes back to, now in the interrupt initiated IO, if the operation is not complete, then it will go off to, it will not go back here because the device will interrupt it. It will go back to the original program that it was executing, and then again have to take a branch to transfer the next data word, right? So in DMA, what we do is we employ what is known as a IOP. IOP stands for Input Output Processor. Now, as the name suggests, this is a complete processor in its own right. Okay. Now, what do I mean when I say this is a complete processor? It means that IOP can download its own instructions and execute them just like the CPU, except that CPU is the central processing unit and is also responsible for many other type of programs and the arithmetic and the logical computations. Okay, but IOP can only execute the programs which relate to the input and output. Okay, now what happens is that IOP in this scheme, the CPU just starts the IOP, the IO transfer, by giving a command to the IOP that you please look after this IO transfer. You just complete this. Okay. So the when it starts the transfer, the CPU gives to the IOP the starting address from where the transfer is to be done of the memory and the IO device, and the amount of data which is to be transferred, right? And it gives the command to the IOP. Now the input output processor has to do this transfer. Please see, the transfer is generally between the peripheral devices, that is the IO devices, and the memory, right? The RAM, etc. Right? From RAM, it may be transferred to the CPU, or from RAM, it may be transferred to the storage device. But the essential transfer is generally between the peripheral devices, that is the IO devices, and the memory unit. Okay. So obviously, uh, the IOP requires both the buses, the IO bus, which in this case, for the direct memory access, there is always a separate IO bus, which is attached to the IO processor that supports the peripheral devices, and there is a separate memory bus, right? Now, for the duration of the transfer, at least the IOP needs the control of both the buses. IO bus in any case is under IOP's control always. But the memory bus in general is under the control of the CPU because it is executing many other programs with the help of the memory unit. So for the time of the IO transfer, the IOP asks for the control of memory buses from the CPU. Okay, this is known as the this is said to be the bus request issued by the IOP to the CPU, and bus grant given by the CPU to the IOP. And generally, this bus grant is only for one or two time cycles, okay, during which the IOP completes its process. Okay. Now, if this bus grant is only for one or two time cycles, this is known as cycle stealing. Why is it known as cycle stealing? Because if overall you see, it feels like that the CPU has had the memory bus for forever. Okay, and in between, it seems like the IOP just came for a cycle or two and stole the buses. Okay, so it is called as cycle stealing. Now the other way is that the CPU the CPU grants the buses to the IOP for a longer duration. That means a lot of uh, mm, transfer is to be done. There is a large amount of data which is to be transferred, and therefore the processor needs to give the control of the memory bus to the IOP for a longer duration. Then it is known as burst transfer. Then it is known as burst transfer. Okay. So I'll repeat. IOP always has the control of the IO bus, needs to have the control of the memory bus. Now, this uh, transfer of the buses from the CPU to the IOP, it may be given only for a single or two cycles. It is known as cycle stealing. But if it is given for a longer duration, it is known as burst transfer. Okay. Now this flowchart details to you the communication that I just briefed you. So initially what happens is that the CPU checks the IOP path by sending this instruction, by sending the test IOP path. That means whether the IOP is ready to do a IO transfer. For example, it may already be doing another IO transfer, right? And the IOP transfers its status word to the memory location. So what does the IOP do? Just like the interface register of an IO device, the IOP also has the status words which tell the CPU that what is the status of the IOP, whether it is free, whether it is working right, there is some problem with some IO device, things like that. So that status word is transferred to the CPU. If the status is okay, the CPU sends the start IO instruction to the IOP. Okay, it sends this instruction that you start the IO. And now what does the IOP do? It although this figure doesn't mention, it also sends the, as I told you, the address of the starting address of the memory location from where the data transfer is to be done, and the peripheral device, the address of the peripheral device between whom the data transfer is to be done, and also the amount of data that is to be transferred to the IOP. The IOP accesses the memory. Now, this doesn't show you the bus grant and bus request things. But after this, the IOP asks for the request of the bus to the CPU, which the CPU grants through a bus grant. And then the IOP uses the memory buses to access the memory for the IO program. So I told you that it downloads its own IO program, decodes them, the instructions, and executes them. After this, now once the CPU has told this IOP to do the IO transfer, it goes on to do its own work with the other programs. Okay, and in the meanwhile, the IOP conducts the IO transfers using the DMA. DMA means direct memory access, where the IOP can directly access the memory without the intervention of the CPU, and prepares the status report of the IO transfer. For example, whether it was able to complete it, whether it was successful or not, or there was some problem with some IO device or memory or something like that, whatever status report is there, and then it interrupts the CPU. After the IO transfer is completed, it interrupts the CPU. Then, when interrupted, the CPU requests the status of the IOP, that whether the IO transfer has been completed or not, and transfers the status word back to the IOP. Okay, the IOP transfers the status word with this report, back to the CPU, and after that, the CPU can continue with the remaining jobs, because now the IO is done. Okay, so this is DMA, and please, you should note that although we have talked about, the CPU doing simultaneous work even in interrupt initiated IO, but if you are asked that what is a truly concurrent technique, that means which technique allows you to process other tasks simultaneously with a IO program or a IO service routine, then it is DMA. Okay, because here CPU can very freely, uh, parallelly process the other tasks along with the IO program. Okay. Now this completes chapter number 11. Okay. Now there is a small section that I want to do, pipelining. I'll be sharing my screen. Please let me know when it is visible. Is there any problem? Is there any problem in what we have discussed so far?
No, ma'am.
Good. This is very important. So sometimes they may directly ask you what is DMA, what is the difference between these three techniques, or you may be asked in other ways. For example, which technique does the CPU always have to keep on checking the system, and or which what is the most technique which allows the CPU to concurrently execute the other programs along with the IO devices. Explain the technique. If you ask to explain the technique, then you should give the block diagram of the DMA and also maybe this CPU IO flow chart that I showed you. Both these figures, okay? Depending upon the marks, obviously. If a full detail is asked, then you give this interface with this interaction also. Now, okay, before I proceed to pipelining, there is something that I wanted to just discuss here with
Ma'am,
you. I
pipelining is a new chapter.
Pipelining, yeah, we only have to do 1 or 2 sections there, so it should take us only 10 minutes. Okay.
Okay, ma'am.
Now, please see, this is what I've already done with you. Fixed point representation, chapter number 3, I did with you, right? All these representations and all, and then these computations. So I just wanted to pause here and tell you that these type of computations are very important from the point of view of the exam. Okay, so I'll take a revision class. Today I just want to finish with the topics, and I'll take a revision class. Maybe I want to take a revision class maybe Friday or Saturday, uh, wherein I can, just do some questions with you and tell you some topics that you should focus upon, that you should definitely not leave, or you should focus more upon from the examination point of view. Okay, so this is one such thing, this kind of competition. So +6 +13. So this is simple. You can see this is simple addition, uh, uh, where the numbers are represented in the sign magnitude form. In the sign magnitude form, the number is written as it is. Only the leftmost bit indicates a 0 if the number is positive, and if it is negative, then it is 1. Now, when we have to do something like this, please see, when one of the numbers is negative. Okay, so when one of the numbers is negative, such as this, or this, or this, where both the numbers are negative, the negative numbers are always generally represented in the 2's complement form. I told you this. So I'm just repeating this. So whenever I have to do -6 +13 means 13 minus 6 only, right? So how to do? We take 2's complement of 6, add it to 13, right? And whatever is the answer, if we don't get a end carry, that is the answer. If we do get a end carry, then I'm sorry, when we get an end carry, we just discard the end carry, and that is the answer. And when we don't get an end carry, we take the 2's complement of the answer again. Okay, So the same thing happens in all these cases, okay? But you should practice this. This is what I'm just trying to tell you. And similarly, this is the computation with the twos complement, right? Similarly, you should also do for binary, okay? Decimal, I'm sorry. So things like this. Mm, I'll just show you. Things like this. This is in BCD. What is BCD? BCD is nothing. BCD is simply, please see what is BCD representation. I think I did that with you, but did I?
Binary coded something था कुछ.
Yeah, binary coded decimal. We did it, I think. Okay, so please see, these are the BCD numbers. So for the first nine numbers you see, they are represented by a 4-bit binary code. That is all. So for example, 7 will be represented as 0 1 1 1. Okay, and 2 will be represented as 0 0 1 0. Okay, and so on and so forth. Okay, now what happens from 10? Otherwise, what is the binary equivalent of 10? What is the binary code for 10? It is 1010, right? But in BCD, what happens is as soon as we go on to double digit or 3-digit numbers, we still follow this format. So this becomes 0001 for this digit 1 and 0000 for this digit. Okay, so that is the only. Similarly for 248, you can see that this is 2, then this is 4, then this is 8, right? So this is the BCD number. Now for decimal numbers, you may get, plus minus, doing plus minus using 10th complement or using BCD numbers. So here, please see this. I'm just, I just encountered this, so I thought I'll just stop by and show you this. Okay, I'll just come to overflow 1 minute. So what happens if I have to do something like this in BCD? So 0375 plus, we have to do this, right? We have to do this. So how will we do? Please see, actually this is what they want to do. This is what we have to do, okay? So we take tens complement of this, okay, which comes out to be this, which comes out to be this. So now after taking the tens complement, now we have simply converted the numbers into their corresponding BCD numbers. So this is 0 3 7 5. You can see that, right? Yes or no?
Yes, ma'am. Yes,
Yes,
ma'am.
ma'am.
This is 9, this is 7, this is 6, this is 0, right? And then we simply add, जैसे हम the simple binary addition, right? So this is it. So you should not get confused if you get a question saying add two numbers in BCD. It is simple, this addition. Nothing, difficult about this. The only thing is that you should have had ample practice with your hands. So I have also sent you the solution manual for this textbook of yours, so that you should solve the back questions. They're very, very important to solve the back questions. So the values are generally changed. Okay, there you can, you also have the solution book now. If you it is very good if you could also look at the numericals from other books, similar books, okay, if you find them online or you have them, or offline if you can find whatever. But at least your textbook, it is very, very important. So you can expect every year we get questions from the back of the book. Just give me 1 second, students. Okay, another thing, important thing is, uh, I just wanted to revise with you this overflow detection. Now, how do we detect the overflow? Please see. Now, suppose I'm adding two positive numbers or two negative numbers. We know that that is the only case when we can get a overflow. Uh, right, because otherwise it will be a subtraction. One of the numbers is positive, one of the numbers is negative. It will actually be a subtraction, right? So there is no uh, chance that it will be a overflow kind of a condition, right? Now, in both these cases, please see how to detect if there is a overflow or not. So we are doing all, the simple binary addition here. Okay. Now, how to detect whether there is a overflow? If both the carries that are coming out from the last position and from the uh, second last position, okay, if they are not equal, if they are not same, then uh, we say that an overflow has occurred. Actually, an overflow is always there when both the carries are not equal. That means, for example, you can see here 1 plus 1, 0, right? And the carry is 1 here. And when I add this, I get 1 and 0 carry to the next. So when I compare these last two carries, they are not same. Okay. Similarly, here again, they are not same. So in both the cases, there is a overflow. Overflow means simply means that the number of bits that can be stored in a particular register is exceeded. Now, for example, please see here. This is a 8-bit register which is shown to us. Okay, so its normal range will be uh, 0 to 256. That means 0 to 2 raised to the power of 8. But if I reserve this bit for the sign, then I only have 7 bits left. So the range reduces from minus 127 to 128, right? But you can see that the answer which is coming here is 150. Since the maximum number that can be stored here is now 127 or 128, whatever, then this definitely indicates a overflow condition, right? So uh, how to detect the overflow? An XOR gate is generally placed between these two carries. If the XOR of the last two carries which we get is 1, that means there is a carry. When does the XOR gate give us a 1? Whenever the two things are different. And
Different.
yes, and if it gives us 0, then there is no overflow. Okay, so again, this is very simple but very important. It is generally asked, will you get an overflow? So you are generally asked to do a computation plus minus, and then you ask, is there a overflow? Detect, how will you detect an overflow? Okay, yeah. Now there is this small 2 minutes topic that I wanted to discuss here before I go on to pipeline. This is called floating point representation. Now, what do we mean by floating point representation? Floating point representation means that suppose this is the fraction, this is the number that I want to store, okay, in my register. Now, as we discussed earlier, The point itself is never stored, it is always assumed. Okay, so what we do is we generally assume that this point is located at the leftmost position. Okay, so to mm, make that happen, we adjust the value of this number so that it transforms into this form. So how will I do that? This is actually equivalent to this. Yes or no? When I take the decimal, see, I'm just taking the decimal 4 points to the left. So I need to multiply it with 10 raised to the power of 4. Okay. So what we do is instead of storing the decimal itself, we store this number, this value, and we call it as the mantissa. We call it as the mantissa or the fraction. And this part, that is plus 4, we call it as the exponent. We call it as the exponent. So, in other words, I can say that that a floating point representation of a number has two parts. The first part represents a signed fixed point number called the mantissa. This is the mantissa, okay, represented by m, okay, into radix, whatever is the radix. For example, the radix here is 10, so 10 is to the power of plus 4. And the second part is it designates the position of the decimal point or the binary point if we're talking about the binary numbers, and is called the exponent. Okay, so you are already aware of that this can be transformed into this. We are just redefining it here. Okay, this part is known as the mantissa, this is known as the exponent, right? Now, sometimes what kind of questions do you get in this? So the kind of questions that you get in this are, for example, that you have this binary number, okay, and you have a 8-bit register to store the mantissa and an 8-bit register, let's say, to store the exponent. So what will be the values of the mantissa and the exponent? Or they will say represent this number as a floating point in the floating point representation. So all you have to do is that you have to uh, uh, give the value of the mantissa and the exponent and say that this is actually equal to this. Okay, right? Now, when we do this transformation, if the first digit after the decimal is non-zero, then we say that the mantissa is normalized. That means, see, most effective. Okay, so the most effective way is to shift the decimal so that the first non-zero digit is the first digit after the decimal is non-zero. Okay, so you just need to know this term, what is normalization. So normalization simply means that the floating point number is called normalized if the most significant bit, that is this bit after the decimal, is of the mantissa is non-zero. Okay, this is it. Okay, and these are things which are very important, and that is why I am, revising them with you, kind of. Okay, yeah. From this chapter, pipelining and vector processing, we need to do section 9.1 and 9.2. So, what is parallel processing? See, there are four categories of how a computer can work in parallel. Now, what are these four categories? So, the first category is SISD. SISD means single instruction, single data. So, there is a single, you can see here, can you read? Visible to everybody? Yeah, SISD. So the first is single instruction, single data. So here we are generally talking about a von Neumann kind of a architecture that I explained to you earlier in one of my introductory classes, where we have a single control unit, okay, and a single ALU and a single MU. Okay, so one control unit, one ALU, one MU. Okay, so one instruction is executed at a time, that means sequential, and there is no parallel processing. Okay, uh, generally, and if the parallel processing is to be done, it is done by pipeline processing. Okay, in SISD kind of systems. What is pipeline processing? I'll be talking about uh, in another 2 minutes. Now, the next category is SIMD, single instruction multiple data. Now, what do we mean by this is that there is a single control unit but multiple ALUs. Okay, so for example, if we had to perform a computation, let's say on 100 numbers, the same computation on 100 numbers, then one way is how we do it. We store all those numbers in a array, and then one by one, we perform the computation on them. Okay, that is the SISD mode, right? That we use, right? Our systems are SISD, but there are places which require very fast functioning. Okay, for example, robotics, or you know the aircraft control system, or the satellite control systems, or fighters, and places where the decisions are to be taken in a split of a second. These computations are to be done in parallel. Okay, so in those kind of places, parallel systems are used. So SIMD is the first of the kind of parallel processors that we can talk about, that we can think about. This classification of SISD, SIMD, MISD, it has been given by Flynn. So sometimes you ask, what is the Flynn's classification? Okay, so according to Flynn's classification, this is the first of the parallel processing system. The SIMD means there is one control unit, but there are multiple ALUs. So suppose I have these 100 numbers which are on which a particular computation, the same computation has to be done. So instead of doing it sequentially one after the other, we have, let's say, 10 ALUs performing at the same time. So 10 of them can pick up the first 10 numbers and compute the results. Then the next 10 numbers, and the next 10 numbers, while the single instruction which is to be performed is given by the CPU, by the single control unit, and the control of all these ALUs is still maintained by it is being, all these ALUs are monitored by the same control unit. Okay. Now the next category is MIMD. MIMD is the category to which most of the multiprocessor and multi-computer systems belong. Okay, So the examples of MIMD computers are multiprocessor and multi-computer systems. Now, what are these? These simply mean that uh, MI multiple instruction, MD multiple data. Okay, so not just the multiple ALUs, but there are also multiple control units. That means we have complete multiple CPUs. So there are many CPUs, multiprocessor systems, multiple processor systems which are working together to solve a particular problem. So what is done is, suppose there is a big competition, it is divided into, let's say, those 100 numbers or 1000 numbers that we had are, and we suppose have 10 processors, then they are completely divided into 10 parts, okay, and given to each of the CPU for processing. Now, or we may not now even have the single instruction. We may have different instructions to be run on different set of numbers. So one of the CPUs can pick up the first instruction and do the computation, while the second one will pick up the second instruction and do the computation. So a job division is done and handed over to the processors, which uh, work like a single system in the sense that they solve the same program and give the result together. Okay, so they work as a multiprocessor, multi-computer system. Then the fourth category in this line is MISD. MISD means multiple instructions and single data. So that means multiple control units and single ALU. This kind of a system, please see, is theoretically not possible. It is theoretically not possible. Okay. So what will be the use of having multiple instructions but only a single ALU to complete, right? The instructions will not only be able to complete, right? Now, we are going to look at pipelining. So what is pipeline? A pipeline can be visualized as a collection of processing segments. A pipeline can be visualized as a collection of processing segments where each segment performs some partial processing. Now, have you seen the place where the cars are serviced? What happens there is a big assembly line, and that is why this pipelining is termed as pipelining. The term is taken directly from the assembly lines which are there in the production houses, or for example, I'm telling you about a line in let's say where our cars are serviced. So what happens is that first of all, suppose the cars need to be dusted. Okay, so only maybe dusting is done, and then after that the car is washed, and then after that it is scrubbed, and after that its fuel etc is checked, or various parts are checked whether they're working right or not. After that, we fill in the oil, the engine oil, okay, and the water in the. So these things are, let's say, done. Okay. So now, what will be the sequential normal processing? A car comes in, it gets dusted, then it gets washed, then it gets scrubbed, and then passes through all these stages, right? Then when the first car is finished doing all this, then the second car comes in and starts getting processed in all these stages, right? Although you can see that, in practice, this will not be the most efficient way to do it. Okay, what generally happens is that the first car of the day, it is dusted and put onto the washing segment. At the same time, a new car which is received is put onto the dusting segment, right? Now, when the first car is finished with the washing, it is advanced to the scrubbing section, that is the third section. The second car comes to the washing section, and a new car can still be admitted to the dusting section, right? So at each of these stages that you see, each of these tasks can be seen as a segment. They are called a segment. Okay, and they are being performed in parallel. So up till here you can see that in the three stages, three different cars are being, serviced at different stages, right? One is being washed, one is being dusted, one is being, let's say, scrubbed, and so on, right? So this, in this way, we don't have to wait for the entire cars to get through, and meanwhile all these segments actually sit idle, right? So this is the job of pipelining. Exactly in the same way, please see, suppose I had to perform this computation, this calculation for I is equal to 1 to 7. Okay, now the sequential way would have been to first do it for I is equal to 1, then for I is equal to 2, then for the, right? Now suppose it takes 1 second for I is for each I, then it would have taken me complete 7 seconds. But now suppose I divide this task into three segments. The first one is where I load AI into R1, BI into R2. Segment 2, we multiply these two and put them into, let's say, a third register, and simultaneously we load CI into R4. Okay. Now in the third segment, we have the result of this, and we also have this available. So we simply add them and we put into R5. Okay. So this is how this pipeline will look like. You can see that these are the various segments. So this is the first segment. Up till here is the first segment where we are just putting AI into this, and second segment, they multiply and put into R3. CI is fed here. The third segment, these two are added and put in R5. Okay. Now let us see the benefit what we get out of pipelining. So you can see that in this diagram, in clock pulse 1, that means in the time cycle 1, only this work will be done, right? But in clock cycle 2, when we have already filled in R1 and R2 and we are proceeding to do put A1 into B1 in R3, at the same time A2 and B2 could be loaded in R2, right? And at time cycle 3, where and C was we've already put in C, right, in time cycle 2. Now in time cycle 3, when we want to add this and this for A1, B1, C1, these two that I admitted in the last stage now move here. They move here, yes or no, right? And these R1, R2 become empty. So I admit A3, B3 here, right? So from third stage onwards, please see, from third cycle onwards, I will start getting a result at each clock cycle. Can you see the benefit? Otherwise, if one segment took 1 second, then I would have had to wait for 1, 2, 3 seconds for the second one to start. Then 1, 2, 3 seconds for the third one to start, right? So after 6 seconds, we would have just begun with the third one. Now after the third second, we start getting a result, and every time we will get a new result, right? So how much wait is there? The number of segments there are that the first set must pass through. That is the only time we have to wait. Okay. So this is the advantage of pipelining. Okay. Now, uh, this is there is a speed up ratio that we can compute with the example that we just saw. Okay, suppose there are k segments. Okay, instead of 3 there are k segments, and each segment takes a time tp. So in one pipeline, in every pipeline the time taken is tp. Okay, and there are n tasks. So in our case, for example, you can see that there are 3 segments here, 1 2 3 segments here, and there are 9 tasks. I'm sorry, there are 7 tasks here, right? 1 2 3 7 tasks here, and let's say they take time 3. They were taking time 3. Now, how much does the first task take time? The first task will take the full time, right? It will take the complete time because it has to go through all the stages with this particular time. So we just multiply this, right? But for the next n minus 1 tasks, every cycle we are getting out one output, right? So what will be the total time? The total time, please see, the total time taken is k plus n minus 1. K plus n minus 1 of tp, right? K plus n minus 1. So sometimes in previous years you've got a question like if there are 4 segments and 6 tasks to be processed, how many clock cycles it will take in a pipeline? So in a pipeline it will take 4 plus 6 minus 1 is equal to 9 clock cycles. Okay, so this is the first kind of numerical that you can expect from this section. Then the other kind of numerical that can be expected is the speed up ratio. So speed up ratio is what? This is the time that we have calculated for the pipeline. And what is the normal time it would have taken? It would have taken for n tasks. It would have taken, let's say, if the complete tasks, one complete task takes tn time, this will be given to you obviously, then it will take n tn time. So we just divide this. So this is the speed up ratio. Okay. So again, there are examples like this in your previous year question papers as well as at the back of the book that you should practice for all these kind of numericals. Then there is also another thing which is very important here, which is called the space-time diagram for pipeline. This is very, very simple. Please see, nothing difficult here. So if there are 4 segments, we list the segments this way, and there are 9 clock cycles, we list the clock cycles this way. And then please see, suppose there are 6 tasks. Okay, so in the first segment, in the first time cycle, T1 is only processed. Then in the second time cycle, this T1 comes here, this comes here, right? This T1 comes here. So this becomes empty, we put T2, right? Then in the next time cycle, this T1 gets shifted here. Then this T2 will get shifted here. And this becomes free, we add in, we put in T3, right? Then T1 gets shifted here. T2 gets shifted here. T3 gets shifted here. And we add T4 to the new slot, right? Now after this, T1 will have completed, okay, because there were only 4 segments. T1 completes, we get T1 out, and then T2 is shifted here, right? T3 gets here, T4 here, and T5 is added, right? So this is what you have to show. So what generally is done, they will ask you that what is the number of segments is 5 or 6 or 3, and the number of clock cycles is itna, and the number of tasks is, let's say, 3 or 4 or 5 or 6 or 7 or 10. So you just have to draw this. Okay, now this is very simple, but again let me tell you that if you don't draw it by your own hand, then you will not be able to do it correctly in the paper. Although this is very simple, please see, there is nothing, there is no complication here. And these questions, for example, a numerical of this sort or this sort, they come 3 marks, 4 marks, 6 marks, this space-time diagram. So these are very, easily scorable marks. Pipelining is a very easily scorable
Ma'am, what
section.
is noted here in this formula?
Sorry, come again.
Ma'am, what is S denoted here in this formula?
S.
Capital S.
S means, S denotes the speed up ratio. This S, you mean to say? Are you asking about this S?
Yes, ma'am.
This just denotes the speed up ratio. Speed up ratio means how much have we speeded up. If we were doing the normal computation, we would have taken this much time, and if now we are using a pipeline, we would have we take this much time. Okay, this is all. Okay, right? Any
Okay,
other
ma'am.
doubt? Any other doubt, students?
Ma'am, what is TN?
These three things are very important. This is important, this is important, and this is important. Okay, all these things are asked again and again in your papers. Huh? Yeah, tell me. Tell me. Somebody wants to ask something?
Ma'am, what is TN here?
Can you
NTP.
just type in the chat box? I can't understand what you're saying. Or increase the volume of your mic, please. Tn is the time, is the normal time taken. That means if there is no pipeline, the time taken, for example, the time taken for a car to go through all those stages in a normal sense. Okay, so there is no pipelining, no other, we are following the normal sequential approach. Then the total time which is taken. Okay,
NTP, ma'am.
sorry, come again.
Um, TP represents what?
TP is the time that is taken in each pipeline. So as I told you, this you can say KTP. So every every segment the time we are taking for each pipeline, pipeline 1, pipeline 2, pipeline 3. So TP, so T1 for this, T2 for this, T3 for this, time taken for this, time taken for this, time taken for this. And what is TN? TN is the time taken for all of them together. It will be generally given to you in a non-pipeline system. Okay?
Okay, ma'am.
Any other doubt? Okay, so we have finished with the course. Okay, I hope you have enjoyed learning as much as I did teaching you. And I wish you all the best. I will take another class after your practicals, Friday or Saturday. I'll talk about all the very important things from the point of view of the examination now. Okay, and point them out to you, maybe go through them, some of the things with you. So please please try to be present for that class, and all the best for your practical. Uh, So whatever you've submitted in the practical file, I told you only similar questions out of that will be asked. So I think in the last class only I told you what you will be required to do. Uh, should I repeat once again?
Yes,
Okay,
ma'am.
let me just tell you once again. So the first question will be to make a machine. Okay, making a machine means making your own registers, memory, the halt bit, the status register. Okay, and then making your fetch routine. Okay, and second question will be to make the fetch routine. It is always second question is always the fetch routine. So fetch routine you have to make, and then you have to third question is that you have to implement the CLA, okay, or CLE, or and or add. Okay, you don't need to accept it from the user, you will be given a value. Okay, so at the level of what you have done in the practical file, same level. So only two or three instructions will be given to you, which you have to implement. This is step number 3. Implement means write down the micro instructions for that and execute them. And fourth step is that you have to mail me the .cpu file and the .a files that you have made. So it is your choice that you make all the 2, 3, 4 micro instructions that I give you in the same assembly language program, or you make different ALP for that. So whatever number you make, you just send them to me, right? So I will, what you have to remember while sending to me is, I will give you a format of the subject line. Okay. So you have to name your files very carefully according to the format that I will send. So along with your practical, I will send that format also. So most probably it will have a roll number, and if there is a set, then that set. Okay, so you just have to look very carefully at the format and follow the convention for naming your file, and put the same thing in your subject and send the mail to me. Okay, so you will be given a time of 4 hours to do this. So that should be sufficient. Okay, so I will simply post the uh, practical assignment, and you will complete it, and within 4 hours you can send it back to me. Okay,
Ma'am,
this is the only thing which is to be done.
ma'am, you mean we are
Yes.
supposed